Yeah, probably we can start now. Hello everyone. The next speaker is Johannes. He will talk about the disproof of the ununiform Littlewood conjecture.
Thank you. Yeah, so the plan of the talk is rather to give some broader overview of Diophantine approximation, and then I think only towards the end I will come to this part of the Littlewood of the uniform Littlewood conjecture. So okay, so I start with a theorem by Dirichlet, 1842. So this is the most essential thing in Diophantine approximation, where everything else kind of starts from. So I write theta usually for a real number. Okay, I have to be a bit careful. In the first part, I should maybe say, let's talk about irrational numbers. Rational numbers are sometimes a bit, with respect to rational approximation, a bit delicate. There are infinitely many integer solutions, or okay, let's write it. It's rational solutions. P over Q is a rational. Yeah, you can think with the lowest terms, of course, to the equation theta minus P over Q. So, let's write it like this: 1 over Q square. So yeah, this is known as Dirichlet's theorem, and many papers as Diophantine approximation have this in the first page. So can I ask who knows about this theorem, has heard about this theorem? Okay, so some at least. Yeah, so in Diophantine approximation, of course, everyone knows it, but yeah, so this is Dirichlet's theorem from mid-1800s, and yeah, as I said, this gives rise to all kinds of things that have been studied. I will discuss some of them as much as I can do in this time, and but what I maybe want to directly state is actually Dirichlet's theorem is a bit more general. So okay, the first part is the same for any sin r. There are infinitely, yeah, and for any parameter q, capital Q greater equal 1, there is a solution to P over Q equal 1 over Q, where, yeah, so P and Q are again, of course, integers, and yeah, Q you can assume positive, the denominator, of course. So this thing has always a solution. This is stronger than this, right? So you can go up here kind of by taking Q is equal to capital Q. So you choose an arbitrary capital Q, and then you can just take small q. You can convince yourself in a few seconds that if you take small q is capital Q, then you get solutions to this. And things like this, the upper part we would usually call ordinary approximation. And things like this with a parameter Q, and then you do something, you range your denominator up to some bound. This is usually called uniform approximation. Yeah, so I think they also did this already in 1842, the stronger one. And yeah, what's interesting is from a historical point of view, yeah, he did both of this in early 1800s, but then until the last, I would say, 10 years, the focus in Diophantine approximation. Until recently was strongly on the ordinary type of problems, ordinary approximation problems that arise of this type where you don't have this parameter capital Q. So I will come to some examples of what we're interested in later, ordinary approximation. So people, but only with recently, so in the last 10 years, more attention has been drawn to uniform problems. Yeah, I mean, I didn't say no what problems are, but so you see already there's a difference, right? This is stronger and implies this, but the other way, not so much. So, yeah, so to be fair, there's some older paper of Davenport and Schmidt. Schmidt is, yeah, I think they say often he's the most famous Austrian mathematician. He's over 90 now, but still alive. In the late 60s, they wrote some papers already on uniform problems, but I think this was just one paper. So essentially, there has not been so much study about situations like this. So, but this has recently, people got more interested in uniform problems. Okay. So this way we has a solution. So let's maybe for the moment talk about ordinary approximation. So we know that we can always solve this inequality. Now it's interesting to see, I mean, can we do a little bit better? So can we, so is it maybe possible to, which is the best rate that we can write here so that it will still be true for all numbers? This would be maybe the first interesting question. Can we write something better than 1 over q squared, something decaying faster? And it's actually true that you can write 1 over square root 5. So this is smaller than 1, yeah, so it's a bit better. This is still true for, yeah, maybe I should also say here, you don't have a problem for rational numbers. This is still true, but here you have a bit of a problem because you could see always the same rational number here, then you cannot write infinitely many. That's why I said it is a bit delicate sometimes to work with rationals. They are not very interesting. So, okay, so that's, usually I want this to be irrational. Okay, so this is, so you can improve actually this one, and this is by Hurwitz. So Hurwitz, I think also 19th century, but later 19th century. And so the theorem says that this is always soluble here. There's always infinitely many solutions. Solutions P over Q and some reduced ratio. And yeah, and the factor and the right-hand side, let's say, just is optimal, which means for me, I cannot improve the factor 1 over square root 5. So this is the best factor with which this works. I mean, the optimality is relatively easy to see. So for optimality, I mean, easy to see. I mean, you can check it. If you know it, it's easy to check it, let's say. For optimality, you can take the golden ratio, I think it is just. So yeah, or 0, 1, it doesn't matter. Or what is the first digit? So I'm not sure if you're all aware of or no continued fractions. So this is should be the continued fraction expansion of the number. So this number, for this number, you cannot do better than 1 over square root 5. So what is continued fractions, if you maybe don't know that? So every real number, maybe I write now x instead of theta, can be written in the following form. A0 is kind of a special rule, it's just the integer part, a1, a2, a3, and so on. Yeah, if it's a rational number, then it would stop at some point. It's finite. Otherwise, it's an infinite. Let's say x is irrational, then this is really an infinite sequence. And this is another notation for a0 plus 1 over a1 plus 1 over a2 plus 1 over a3 plus, and so on. And if you stop at some level, then you get an approximation. So let's say you stop here with this plus 1 over a3. You can write this, simplify this a little bit if you want. But anyway, it gives you some rational approximation to the number. So these are integers, AI, positive integers. Yeah, these continued fractions are very important for Diophantine approximation, because as you can already see, maybe from this example, they tell you much about the approximation properties of a real number. So essentially, you see, you do take the least quotient that you can take everywhere. So one period, then it gives you also kind of the worst approximable number, where this constant cannot be improved. For every other number that does not have this infinite one pattern, you can improve the square root 5 a little bit. And there's I would say bigger theory about this. Yeah, so yeah, I'm not sure how much I should say about it, but in general, it is true that the following theorem, which again shows how connected continued fractions and such approximation problems are. Maybe I write here the definition for the moment. So psi real number, again, let's say it's irrational, is called badly approximable if psi minus p over q is greater than some constant over q squared for all pq integers. I mean, I should avoid the trivial choice that yeah, I mean, q cannot be 0 when I write it like this anyway, so I think it's okay to just write it like this. Yeah. So there exists some. This is true. And so for some constant, you have this. So for example, for this number with the ones, you can choose any sequence, any constant that is a little bit smaller than 1 over square root 5. So it is, yeah, the theorem before from Hurwitz tells you that 1 over square root 5, the c must always actually be smaller. Okay, smaller than 1 over square root 5. But let's say, to be safe, lower or equal, probably strict lower would be okay. This must always be the case by, oops, so. Yeah, smaller than 1 anyway, already from Dirichlet, but actually 1 over square root 5 is even true. So this is, yeah, so this is kind of the terminology is clear, right? It's badly approximable, because the most thing you can do, I mean, the least you can step down is by choosing a smaller constant, right? But still have basically the order 1 over q squared, but just with some constant. And yeah, and we see that these badly approximable numbers exist, right? This is one example, and actually the theorem, who is this actually due to? Maybe I cannot think of the name, but maybe later I will find it. So the theorem says z theta is badly approximable if and only if the AI are bounded in the continued fraction expansion. So these very badly approximable numbers are exactly the ones that look somehow like this, right? So that where you don't have any subsequence that goes to infinity. And you can also give some bound of how if you have AM bounded by some constant, then then you can say something about the constant. But I will not write down these estimates exactly. Is this Hurwitz, or I think this is not Hurwitz, but anyway, so this is a well-known theorem. Yeah, so the continued fraction basically tells you how well approximable a number is. And what we know about these badly approximable numbers, yeah, so there are actually not too many of them. So a generic number will not have bounded continued fractions. So the Lebesgue measure of the badly approximable numbers, I just write capital bad. This means the set of badly approximable numbers is 0. So it is, in measure terms, it is a small set. But on the other hand, it's not too small either, but the Hausdorff dimension is full, which means it's 1. So I hope you have an idea of Hausdorff dimension. So it is just some general dimensional concept that the dimension don't have to be integers. So, for example, the Cantor set, the classical Cantor set has Hausdorff dimension. What is log 2 over log 3, I think. So the classical Cantor set is you start with 0, 1, and then you, in the first step, you throw out the middle interval, and you take these two subintervals, and then you do the same in the next intervals. So this will be like 7 over 9, 8 over 9. And here again you have two subintervals, 1 over 9, 2 over 9. So these 4 subintervals, and you do this infinite process, and in the end you get some totally disconnected set, some fractal set. And for example, it would have dimension strictly between 0 and 1. This would be the exact dimension. So yeah, I don't want to define Hausdorff dimension now precisely, but it has to do with covering and so on. But yeah, anyway, it is some measure for how big a set is that is a bit finer than Hausdorff than the Lebesgue measure. When the measure is 0, then what we usually care about is maybe the Hausdorff dimension is at least big, or so the next level after a set is small in the Lebesgue measure 0 sense is to go down into the level of Hausdorff dimension. Yeah, the measure, the Hausdorff one-dimensional Hausdorff measure would be 0 because this is equivalent to the Lebesgue measure. But yeah. Okay, but so it is relatively small, but not too small either. Yeah. And yeah, so this is one thing that's always interesting to us in Diophantine approximation, badly approximable. Then there's the other side that maybe right here. So you can think of, let's say you want to have an extremely well approximable numbers. So for example, 1 over q to the mu, and you think of mu something very large. And so this would be the other side of the spectrum, but you're interested in things that are very well approximable. You find some very close integers, and it's not hard to construct something like this. For example, this is this Liouville constant, n to the minus n factorial, which has ones in the decimal expansion at very distant points at n factorial, and otherwise zeros. If you truncate it, so this will be something like this. At 6th position is a 1, then only at 24th position there's again a 1. So if you truncate this series after some 1, then you see a long block of zeros, and this is why you can check that this number is very well approximable. So this is what we would call a Liouville number. Yeah, this is the Liouville constant, and something like this is called a Liouville number. A Liouville number just means that you can take mu is infinity. Then you, okay, well, maybe I should write it here. By definition, that you can take mu is infinity and you get infinitely many solutions to this. Yeah, and okay, and these are also very small. So again, some theorem. Who is this? This is actually, it follows from easily from Khinchin's theorem. Khinchin, 1924, if I'm not wrong. Is that, yeah, actually something much stronger. So in particular, Liouville numbers have measure 0. Okay, the back measure 0. So they are also small. So yeah, which just makes sense that you wouldn't expect too many numbers to be very well approximable. Measure 0. Then again, you could go down and ask, okay, if the measure is 0, the Hausdorff dimension can still be optimal, can still be as large as 4, as 1. But in fact, this set has Hausdorff dimension 0. Zero. So it is really very small in a metrical sense. So even if you go on this final level of Hausdorff dimension, it is, you don't see many of these numbers really. Yeah, I should say the second part, this is actually follows rather from Yannick, an improvement or a refinement of Khinchin's theorem is Yannick's theorem. So the back measure 0 follows easily from Khinchin. This I should refer to Yannick probably a little bit later, but I think like something like 1931.
The continued fraction of that number, easy to understand.
This is a good question. I mean, you see many good I mean, these truncated things are convergence, but they are not all convergence. So you see, if you, so this, let's say you truncate here, then you get the number 110001 divided by 10 to the, what is it, 6 or something, yeah? 10 to the 6. This would be a okay, I didn't define convergence, but if you stop at level n, let's say 1 over a0 plus 1 over, let's say plus 1 over a2, this you would write p1 over q1, or with the 2, maybe you would write p2 over q2. Anyway, if you stop at some point, this will be a good approximation, rational, so this will be a rational number, right, if you transform it, and this is a good approximation to the number. So yeah, basically every good approximation comes from some convergence, a bit, yeah, sloppily, but essentially it is true. So for the good approximations, you study this convergence that come from finite things here, and this would be a convergence, for example, of this number. So whenever you truncate, you see you have good convergence, but they are not all. So there are other convergences that you don't see so well, and that are not so good. So not every convergent of this number would be a very good approximation. And there's something called how do they call it? The so some relatively famous lemma. Okay, I cannot think of the name, but anyway, so it is possible. The answer is it is possible to write explicitly the continued fractions for something like this. It is possible, but not every. So you see the good convergence somehow by truncating, but they are not all. There are some numbers which have something between, for example, between 10 to the 6 and 10 to the 24. This will be two denominators, but you will see some other convergence with denominators in between that are not so well approximated. And yeah, I how is this lemma called? I just want to think of this now. Then. Okay, I later maybe yes, so yeah, here, yeah, this is more digit based, as you can see. Yes, so the question is good, of course. So how does this relate to continued fractions? And yeah, so I think I hope this answer explains it a bit. So it is generally a very hard question to go between base expansions and continued fractions. So here it's still possible that there is some kind of trick how to do that. But if it's not that nice, in general it is tough to say something. Yeah, to have a number in some base, and you want to know about the continued fractions. This is normally a very tough thing to say something about that. But it's not quite the direction I wanted to talk today. But yeah, it's good to point it out. Yeah, actually, what I wanted to say also is this Khinchin theorem. Yeah, you see that actually the claim is much stronger. Host of dimension 0 is much stronger than just the back measure 0. And actually, the Khinchin theorem says something. So let's write again Khinchin. Something much more precise about the back measure statement. So even something like this, you want this infinitely often, let's say. 1 over, you have to, okay, I have to be careful now. So if you have, for example, something like this, you want this infinitely often. So you want infinitely many rational numbers which approximate a little bit better than the Dirichlet bound. If you write just the constant, then it still has full measure because base is very small. But if you write something which goes to infinity but rather slowly, this will already has the back measure 0. Okay, but if you would not write the square here, you would just write 1 over log q, then it would have infinite measure. And really, there's some more general principle than I wrote here. So basically, should I erase now? I will not erase it. So it depends. If you write something like this, I think 1 over q you must take out. That and then. Yeah, just it's a bit not to get confused with the q powers, but it depends. So if you write something, if you want something like this, lower than phi of q, so phi is some function from the integers to 0 infinity. Then this you want this infinitely often, so people often just write infinitely often, meaning that you find infinitely many such solutions in P and Q. So this set has the back measure. And then yeah, you have this distinction. It has either 0 or, I mean, yeah, depending how you write. If you just restrict to the unit interval, then you write 1, otherwise you have to write full measure, depending on the convergence or divergence of this series. But you have to be a bit careful when I write it like this. I have to multiply with q, right? So I have to write here. If I write it like this, I should write. Okay. Sorry. Okay, I should write it here. Okay, sorry. Okay, so phi is a function going to 0 infinity, and you have this. The theorem says phi of q infinitely often has the back measure equal to, yeah, so I restrict my numbers now to 0, 1, so that I have the natural measure of 0, the full measure is 1, is equal to 0 or is equal to 1, depending if some psi of q times q, I think I have always getting confused with the powers, but I think this should be the correct way to write it here. If this is, so it has 0 measure if this is, so if it goes fast enough that that this converges, right? So converges, and if this is infinite. So depending of divergence or convergence of some series, this will have infinitely many solutions. Yeah, there's okay. In a Diophantine approximation conference, the people would already correct me because this is a slightly imprecise. There's some delicate thing about this phi should also be decreasing to have this nicely. And there's some very big, some recent work by Meinhard and Kofolopoulos who solved the so-called Duffin-Sheffer problem, which was also open for like 70 years. Duffin-Sheffer problem, but I don't want to talk in detail about it. It is about non-monotonic phi. Functions phi. So it turns out this theorem is not quite true if phi can oscillate. This is really a delicate thing, and instead Duffin-Sheffer proposed some term where the Euler phi function somehow comes in, and yeah, this is, as I said, only recently solved by Kokolopoulos. I don't know how to exactly write this Kokolopoulos. Something like this, and Meinhard. So yeah, probably you've all heard of Meinhard. So this is, yeah, it is some delicacy on phi, but there was an Annals paper or so some big result. But yeah, but for decreasing phi, it has long been known. So if you choose some rather nice phi, then the classification is really like this. Otherwise, the formula looks a little bit different. And yeah, it's interesting, but a bit more for specialists. Okay, so this is a bit of a general topic, general introduction, what we're interested in and why we also care about logarithms and lower order terms, right? Because it makes a big difference if you write some log factor here or not. You can make this series by choosing some different exponents here. You can make this series convergent or divergent, and the behavior is very different. So from the metrical theory, this is, yeah. And there's nothing in between. So it's a general phenomenon. In Diophantine approximation, you usually have this 0-1 loss. Or here I have it. That things are either 0 or 1 in measure 1. You don't have things where things are in between. This doesn't occur. So yeah. Okay. Yeah. What is also maybe interesting to note, so this was all about this first type concerning ordinary approximation. What I should also say is here in the uniform case, things are a bit different. So for uniform approximation, so there's a theorem easy to prove by Khinchin, also 1920s, I think, or maybe 30s, that so there exist. So okay, I should say okay, that psi be an irrational real number again. For rational things are a bit strange, but then for arbitrarily large Q, we have psi minus P over Q is always greater than 1 over 2QQ. So basically there's a factor 1/2 that you have to admit, but then basically this theorem is always close to sharp. So for certain parameters, capital Q. So yeah, and I should say for all, yeah, again, of course, Q is small q always should be bounded by this capital Q. So very different from here, right? You have some numbers that are badly approximable, but there are also some Liouville numbers which are very well approximable. But something like this in uniform case doesn't appear. So yeah, up to a factor of 1/2. Dirichlet's theorem in the uniform version is always for each number basically correct. I mean, they're the correct one. So really, this is very, in some senses, these are very different problems, uniform and ordinary problems. And it's, yeah, a bit of a mystery why it took so long until people got really more interested in this uniform theory. And basically for many decades, only this thing was the ordinary approximation was studied with, yeah, maybe a few exceptions. Any questions so far? Yeah, so I think then I would close the introductory part and come a bit to multiplicative approximation and a bit more to the direction of my paper. Yeah, I think I will erase here maybe. What do I need? I think this I want to keep. But I think maybe I leave this also.
You can use that board as well.
Okay. Yeah. Yeah. So something people got interested in are multiplicative problems. And let me maybe directly come to the not theorem. It's a conjecture by Littlewood. That is, maybe some of you have heard of. It's rather famous. In Diophantine approximation, people know it, of course. Littlewood, around 1930. And it says the following: for any, yeah, I mean, everything I did so far, I should say, is for one number. So you have a single number and you want to approximate by rationals. Before I come to multiplicative stuff, I should say, according things for higher dimension would look like that: a simultaneous approximation where you want something like this: maximum of Q, let's say theta 1 minus P1, and Q theta 2 minus P2. You want this to be smaller than, let's say, some negative power of Q. And the natural Dirichlet exponent would be, in the two-dimensional case, it would be 1/2. So this, okay, yeah, okay, here I wrote it in linear form. So if you think of this multiplied by Q, right, then this Q is not here anymore, or maybe better here. Let's say here, this Q square would just become a 1/Q. Right? So in a linear form notation that I will use from now, you have to think of these two always being a 1. But if you have two numbers and you want to approximate them by a rational with the same denominator, so this is the usual setup that we take, then if you have two numbers, then you don't get Q to the -1, like in the theirs, but you get Q to the -1/2. Or if you have n numbers, so you can think of n linear forms like this, then you get Q to the -1/n. So it becomes much worse, right? But yeah. So these numbers get, of course, when you approximate more, then you cannot expect the same rate anymore. So yeah, and then there's also everything you do for, like in the one-dimensional case, you can also do here. You can ask, what constant can I write here? And I think this is, even for the two-dimensional case, not known. So these are tough problems. But yeah, but as I said, this is not the direction I want to go for today.
Is that saying that if you take any zeta 1 and zeta 2,
yeah,
there's infinitely many Q's and P's?
Yeah.
And...
Yes, so you can always satisfy. So for one variable, you can always satisfy, let's write it maybe in the linear form, P theta minus Q plus theta minus P, smaller 1/Q, Q to the -1. And if you have two numbers with the same denominator, then this will only be 1/Q to the power 1/2. So infinitely many solutions, yeah. In triples, so yeah, so infinitely many integer triples, P1, P2, Q, and set Q, yeah, of course, Q should not be 0, and these trivialities we exclude. But yeah, so the exponent will depend, is in general 1/n if you have n such things. But here we take the maximum. So this is maybe the most natural thing, to take the maximum or take any norm of this. But what is also interesting is multiplicative problems. So here's a different you study something like okay, let's write alpha and beta now for the real numbers. Alpha q minus p1 times beta q minus p2. So instead of taking a maximum, you take the product and you ask how big will this be. And it turns out that, yeah, I mean, the thing is you can always make each of them trivially smaller than 1/2, right? By just taking the p, the closest integer to alpha q, whatever q you take. So of course it gets easier to make this small, right? When you have more numbers, then it's easier to make this product small. And accordingly, the Littlewood conjecture says for any alpha beta real numbers, do we have that, yeah, lim inf q to infinity of q times q alpha. So this double bar means I just hide this notation. This means the distance to the closest integer. Do we always have that this is 0? Oh, okay, otherwise it's a conjecture, then don't need the question mark. Yeah, so it looks at first sight like maybe not so difficult, right? Because we know that this is always, by Dirichlet's theorem, you can always make this smaller than 1, and you can make this smaller than 1/2. So clearly this product will always be smaller than 1/2, and for many q's. And then if you think in general, it will probably be true that sometimes this will be closer to an integer, or that you can approximate here a bit better. So it makes sense to consider or to conjecture that this might always be 0. But this is a big open problem in the Diophantine approximation. Yeah, so for almost 100 years now open. Yeah, so it looks like almost true, but it is not so clear. So the best result in metric terms we have is from Einsiedler, Katok, and Lindenstrass. So the next Fields medalist is Lindenstrass. They proved that the counterexamples to this Littlewood conjecture have Hausdorff dimension 0. So they are in R2 this is, right? So this is now a 2-parameter problem. So very little pairs in the plane can have a positive lim-inf. So, and yeah, but it's still not known if it's empty. It's very small. Actually, even a bit more is shown in this paper, but I don't want to go into too much detail. But this is a strong result, but still it doesn't answer if there may be a small set. Like also the Liouville numbers, right, are also Hausdorff dimension 0 set, but they are far from empty, right? They're easy to construct. So yeah, so it's still open. And now fast forward to 2025. Bandi, Fregoli, Kleinbock studied the following setup. They studied a uniform setup to this Littlewood type question, this Littlewood problem. So instead of, so you can form, they did it in more generality, but what it comes down to in this special 2-parameter case is the following. Instead of lim-inf, I want to write the lim-sup, and I need a parameter capital Q when I want to make it uniform. Q times, and then I take the minimum of integers up to Q, and then I take again this Q alpha times Q beta, and they studied the set where this is equal to 0. Okay, so So this is of course harder to be zero, right? Because the lim sup is bigger than the lim inf. So if you would write lim inf, then it would really be the same as up here. Again, you could identify essentially the capital Q as the small q, then it would really reduce to this. But by taking lim sup, you make it easier to be positive, right? So you expect rather to counterexamples rather to exist to this. But the theorem of them is that this set has still Fourier-Lebesgue measure. Okay. So the set of alpha beta in R2 has Fourier-Lebesgue measure in R2. So again, so yeah, actually in this case, of course, when you write this, you can also write just limit. But yeah, but let's write it, keep it with the lim sup for the moment. Yeah, so basically still, even if you take this uniform version, which is harder to satisfy, still basically almost all numbers satisfied. And again, it's a bit strange that nobody considered such a setup before, only last year. Anyway, so this was the result, that it is based on homogeneous dynamics, the proof. So yeah, many of the Diophantine approximation results are coming from homogeneous dynamics, which I'm not such an expert on, but Kleinbock is very good in this field. Also, and yeah, these also are all, they are all dynamicists. Yeah, so what I want now, let me come to what I said, what I did. So my theorem from this year. Yeah, so I should say they conjectured according, they called it the uniform Littlewood conjecture, these three authors, that is this equal to zero always, I just tried. So the question is, are there any counterexamples at all? Right? It is certainly a Lebesgue zero measure set of counterexamples, but possibly there are still no counterexamples to this. And clearly also the Littlewood conjecture would even more be true. So this is, it should be false probably, right? But it was not clear to them if there are any counterexamples. So they stated this as the main open problem in the paper, along with the result. And yeah, so my theorem is that the uniform Littlewood conjecture is indeed false. And I could prove that this lim sup, so there exist, maybe I should write, no, okay, or maybe it's written like this, the supremum over all alpha beta. So the largest constant for this lim sup that you see yeah, I could give some bound, which is some algebraic number that is greater than 1 over 188. This is the numerical bound that I got. So I constructed, or more or less constructed, it is like semi-constructive numbers for which this limit is not zero. This is the result. Yeah, in the paper I also did some other results, but this is the main one, and I think I don't want to talk about anything else from my paper. So this is the result, and also and the set of alpha beta with this property, so with this greater than this, or especially greater than zero, is a dense G delta set. This is, yeah, then relatively easy to prove actually, once you know that counterexamples exist at all. It is not so hard to see that it will be a G delta set when you have some fixed number here, and the density comes from my method also rather easily. So yeah, but it's a nice property. Dense G delta, so like for the BR theorem, that's the setup. So it is actually, in some sense, topologically, it is a very big set of counterexamples. Or also metrically, it is small, that is result. Well, what at this point I should maybe also say that the Liouville numbers, where I have the Liouville numbers, they form also a dense G deltas. So you have a similar phenomenon here. the set is very small in metrical terms of Liouville numbers, but they are very large in a topological sense. And the same is true for the counterexamples of Littlewood. Of uniform Littlewood.
So maybe everybody knows, but I forgot. So G delta thing stands for Durchschnitt from the B2?
Yeah, the intersection of open dense sets.
Exactly.
In a countable intersection of open dense sets. Like in the Baire theorem.
Like
when you intersect infinite dimension, you still get a dense set. Right? This is the Baire theorem.
From Baire categories?
Yeah. Yeah, so this is a topologically a big set. Yeah, so yeah, maybe Baire theorem, right? If I don't know, omega 1, omega 2. So you have a countable collection of dense open sets. Then the whole intersection is again dense, right? And that's why you call this dense G delta set, right? So you still get a big set even if you intersect them, right? Yeah. Yeah, so the counterexamples don't only exist, but they are in a topological sense even a very large sets. A very large set. And yeah, I want to, okay, I should soon come to end. So I used, in my proof, I used one deep theorem, which some happened to be very useful in the proof, yeah, of Kontorovich. This is the last thing I maybe want to say. On some, okay, maybe here, right, Zalemba conjecture. So this was also some very big open conjecture, which just very recently has been fully solved about continued fractions. So it says that there is some integer m, some fixed integer. Potentially it can even be as low as 2, but we don't know by now some like this exists, such that for all integers q, there is another integer p, such that, yeah, if you put p over q and write it in the continued fraction, I mean, okay, let's assume it's between 0 and 1, then you don't have the a0. So you write the continued fraction, it is finite, right? Let's say ak, because this is a rational number now, then it stops at some point. This has all continued fractions bounded by some effective constant. And this effective constant is independent of the q, that is the point. So basically, these numbers are all kind of very badly approximable, these rational numbers. So all the, yeah. So the point is, yeah, you find some, so you take 1 over q, 2 over q, 3 over q, up to q minus 1 over q, and it says that for some p, all the partial quotients should be small. So, yeah, and this is the Zalemba conjecture, and it has, as I said, very recently, just after my paper, actually been verified. I mean, it is a big result. And so what did Kontorovich show? Basically that for almost all, they couldn't prove it for all q, but for almost all q, which means for a density 1 set of q, for density set, actually, again, the density 1 set. So actually, again, more, and I also need a bit of a stronger, they give exactly the error term, but for simplicity, let's say, for almost all q, Zalemba conjecture is true. So they couldn't verify it for all q, but at least the set of counterexamples is very low. It's very sparse, and they could take n is equal to 50 in their result. So conjecturally, even m is equal to 2 works for large enough integers q. But yeah, they give a proof for m is equal to 50 and for almost all. And yeah, and somehow I can use their result. I mean, I don't need to go into their proof, which is about SL2 actions. I didn't need to read the proof. Luckily, I could just take their result. And it turns out this fits exactly into the setting of my construction. I can use this at some point. And yeah, this is one ingredient of my proof. Okay. Yeah, I think maybe I stop at this point.
Thank you, Johannes. Any question? I have a small question here. This was 188.
It's not optimal.
Okay.
And actually, yeah, it is a bit of a sad story with this. I found this and was very happy. And then 2 months later, Moschewitin, a colleague of mine, came up with a better bound, subliminal, greater than something like 0.3. It's like one over the golden ratio or something. So significantly better. So you can see that an upper bound 1/2 is always true. That's not hard to see. So it's somewhere in, but he improved this massively with this, and not only the bound, but unfortunately, well, I don't know, maybe fortunately, his proof is much easier. It doesn't need this insert, but it just uses some properties of Fibonacci numbers. He could simplify my proof and get also a better constant. So the truth is somewhere between here and here.
Is it possible to find a specific example and which is quite close to something like this, or is there
You mean
find some specific value?
yeah, I mean, it is both. I mean, both our results are somehow half constructive. I mean, the proof gives you an idea how to construct them, but at some point you need some, in his case, some uniform distribution property, which is not fully effective, I would say. And here you need also something like this, which is also not quite effective, how to find this P. So it is, I mean, yeah, so both proofs are somehow semi-constructive. You get an idea how to construct it, but it's not so immediate to really write down alpha beta concretely, because there's always something hidden where you take some existence either from something like this or for some uniform distribution result. Yeah.
Thank you. Other questions? Let me check if there's any question. No. Oh, okay, if there's no more question, let's thank Johannes once again.